Thanks. It's a pleasure to be here. So maybe 15 years ago, the highest profile applications of machine learning were for doing relatively mundane things. Things like figuring out which of your email messages were spam and who we should show ads for toilet paper to. But in the last decade or so, as technology has improved and our access to data has grown, we've started applying the tools of machine learning to an increasing set of important tasks. So for example, HR departments now use machine learning tools to help make hiring and compensation decisions. Banks use machine learning tools to help make lending decisions. And in a number of states in the United States, including in Pennsylvania, where I come from, tools that are used to predict whether someone, if released, will go on to commit a crime or not, are used to inform bail and parole decisions in the criminal justice system. So on the one hand, this is good, right? Like to the extent that we can improve important decision-making pipelines, make them work better, that'll make the world a better place. But it should also give us a moment of pause, because when human beings are the ones making important decisions, we expect them to respect certain social and ethical norms, things that have names like privacy and fairness. And when we start replacing human decision makers with automated decision-making tools, there's no reason we should stop expecting the decisions to respect those ethical norms. And if you've been following popular accounts of machine learning in society in the last, say, decade, you've come across a steady stream of articles pointing out when tools from machine learning fail to respect these norms in important use cases. Okay, sometimes the people writing the headlines understand the science better than other times, but each of these articles is about like a real use case, something that actually went wrong and caused harm to real people. So what the book is about is the emerging science of how to stop these algorithms from doing things that we view as violations of social norms like privacy and fairness. Okay. So you would be excused at this point for wondering whether it even makes sense to talk about ethical algorithms, ethical algorithm design, because algorithms are, at the end of the day, human artifacts like hammers. And we wouldn't talk about ethical hammers or ethical principles for hammer design, despite the fact that hammers can be used as instruments of violence. Right? If I were to hit you with a hammer, we wouldn't think of that as some moral failing of the hammer. Right? You could attribute the action, the harm, to the person wielding it. Okay, and as a result, we know how to design laws and regulations to prevent people from hitting each other with hammers. Right? We know how to do it. We just, provide disincentives for committing violence with hammers, and that's enough because I can make the choice to not hit someone with a hammer. Right? I understand how to do that. But I want to claim that algorithms, and when I say algorithms, what I really mean in all of this talk are models trained by the standard machine learning pipeline. Algorithms are different in kind than hammers for a couple of reasons. But one of them is that it's much harder to assign blame for a particular misdeed the algorithm might have done to the human being who deployed it. Okay, it's really not the case that when we see algorithms in the wild doing things that we don't like, it's not the case that this is the result of some malintent of an evil scientist or software engineer like hiding behind a curtain. Okay, this is typically the unintended consequence of usually well-trained people applying a standard methodology. So let's just reflect on what that methodology is for a moment. Okay, typically you'll start with data. Okay, it might be data about millions of people. You might have hundreds of thousands of features, and you might understand this data set as well as anyone can understand such a data set, which is to say, you might understand how the data was gathered, you might understand what the features mean, but there's only so much you can really understand what your data set looks like when it's enormous, right? What information it contains. And then you take your data set and you'll apply some optimization algorithm. You'll apply something like stochastic gradient descent, and you'll try to optimize the parameters of some class of models to optimize some narrow objective function, usually some proxy for accuracy. You want to minimize your classification error. And again, you might understand how stochastic gradient descent works as well as anyone does. You might understand your class of models as well as anyone does, which is to say, just at a very local level. Okay? And the thing you get out of this is possibly a vector of hundreds of millions of numbers. Okay? And at this point, even if you have understood, as well as anyone can, every step along the way, it's really hard to say what this trained model, is going to do in every circumstance. And so when it goes on to do some harm, when it harms some person or some group of people, it's not that we can easily trace this path back and say, aha, that was the fault of the software engineer who developed the model. Because at the moment, we don't have a great understanding of how we should go about doing machine learning in a way that respects privacy, in a way that is fair, whatever those words mean. Okay, and so before we can think about writing regulation that's going to require people to embed fairness and privacy into the design of their algorithms, we have to develop a science to figure out first what that means and second how to do it. Okay, so that's what the book's about. So if you want to embed some social value into an algorithm, right, something that we call, things that we use words like privacy and fairness for, you have to be very precise about definitions. Okay, and not just precise in the way a philosopher might be when talking about fairness, for example. You have to be mathematically precise, because at the end of the day, you have to embed a mathematical constraint into the design of your algorithm. Okay, so it's not easy to do, right? Words like privacy, words like fairness, they mean many different things. People mean different things by these words. But there's a community of people who've, over maybe the past 15 years, have been trying to do this, and they've been making progress. So I've put these words in increasing degree of grayscale here, roughly in proportion to how much is known about them. Okay, so it's not that, I don't want to say that we've solved privacy, far from it, but I'll tell you in a slide about how I think privacy is sort of a success case. It's something that we can aspire to as we go further down the list. Okay, I'll spend a lot of the talk today going through sort of a deep dive into fairness. Okay, I'd say fairness, the study of fairness in machine learning right now, it's maybe where privacy was 10 years ago, and we can look at privacy as a guide for how to proceed. When you go down this list further, to start talking about accountability, interpretability, morality, we basically don't understand these things at all, but that doesn't mean that they're not important questions and can be tackled with the same methodology. Okay, so in the book, we devote a whole chapter to privacy. Here I'm going to tell you about it only in one slide, but I want to hold it up as a kind of success story. Okay, and again, I don't mean that it's a success story in the sense that we've solved privacy. I mean it in a more restrained sense, so I'll tell you what I mean. So for many years, the study of data privacy was sort of a cat and mouse game. Okay, some researcher would propose some ad hoc method of anonymizing a data set that started out with things as naive as just removing people's names and social security numbers. And then an attacker would come along and show that, well, that doesn't work. You can cross-reference data sets and you can reattach people's names. Okay, this is sort of a losing game for the privacy team if all they're trying to do is thwart yesterday's attack. There's a lot of things you can do. But after many years of this sort of back and forth with these ad hoc approaches, in 2006, a nice definition was proposed, something called differential privacy. For the purposes of the talk now, you don't really have to know what that is, but if you read chapter 1 of the book, you'll have a very good idea. The point was differential privacy distilled into something mathematically precise is something we might mean when we say privacy. Not everything we might mean, but one thing we might mean by it. And because it was a precise definition, it allowed us to think about how to build algorithms that satisfied that definition and to think seriously about what the trade-offs were. Okay? And then there was about a decade of academic work. People like me would write mathematical papers for other people like me. There really wasn't, it wasn't a technology. It was a mathematical curiosity. But what we were studying was the inherent trade-off for different kinds of learning problems. The trade-off between privacy and inferenceability, our ability to protect the privacy of people in the data and our ability to derive insights from that data. Okay? We did that for a while. But in the last several years, it's really become a technology. Okay, so I was consulting for Apple when they rolled it out as part of iOS 10. Google Chrome also reports statistics back to Google using differential privacy. And in an exciting development, the 2020 US Census is going to report all of its statistical products with the protections of differential privacy. And so it's gone from sort of, an academic topic to a real technology. And differential privacy means something specific. It doesn't capture everything we mean by privacy, as no single definition could, but what it allows us to do is have a meaningful conversation. It allows us to say, well, does your use case, is it captured by differential privacy or not? And it doesn't take a stand on how we as a society should trade off accuracy and privacy. It provides a language for us to have that discussion. Okay. So fairness isn't there yet. We don't agree on definitions, and we're only beginning to understand the trade-offs, but we can still go through the exercise. And I want to start by just giving you some idea of why machine learning might be unfair, because it's not immediately clear if you haven't thought about it before. But here's a cartoon example, and this is illustrating something that happens on real data. So let's pretend we're trying to solve a college admissions problem. Okay, we're trying to figure out who's going to succeed in college. Say, for your favorite definition of success, maybe they're going to graduate in 5 years with at least a 3.5 GPA. Maybe they're going to donate $20 million to the college 20 years down the line. And we've got labeled data, okay, negative examples and positive examples. What we'd like to do is come up with a rule to figure out, well, who are the positive examples. And say we've got two features, SAT score and GPA. So one thing you can notice about this population is that there's a pretty simple rule that does a pretty good but not perfect job of distinguishing positive from negative examples. Okay? Another thing you can notice about the population is that slightly fewer than half of them are positive examples. There's more negative signs on this slide than there are positive signs. And this is one population. But suppose we've got another one. It's here. Well, this is the orange population, and there's a couple of things I'd like you to notice. So first, there's fewer orange points. Okay, the orange population is a minority, by which I mean only that there's fewer of them. Okay? The second thing you might notice is that the orange points here are shifted downwards. They tend to have lower SAT scores than the green points. That could be for any number of reasons. For example, maybe the green points take the SAT 3 times. They report only their highest score. They take SAT tutoring classes. The orange points take it once cold. Okay, that would result in a lower distribution on SAT scores. Nevertheless, we don't care about SAT scores per se. We care about college success. And from the point of view of the classification task, the orange population is better. They're better in two ways. A larger proportion of them are qualified for college. And it's even easier to tell who those are. And yet, when we put these two populations together, and we say, OK, I'd like to train an algorithm, and I'd like to make sure that it's not racially biased, so I'm not even going to show it group membership. I'm going to say, just find me the linear decision rule that makes the fewest mistakes possible. What I get is the decision rule that best fits the green population. It rejects every single member of the orange population. And it's easy to see why that is. If I were to move the decision boundary downwards, I'd make fewer mistakes on the orange population. I'd make more mistakes on the green population. But because there's more green points, that wouldn't be worth it. Okay, so the orange population was better for the task at hand. I didn't try to embed any bias into my algorithm. I just said draw the line that makes the fewest mistakes, and yet I reject all of them because they're a minority population and so don't contribute as much to my overall error metric. Note that if I was able to make decisions taking into account group membership, I could do better. I could have a Pareto improvement here. Okay, so a couple of takeaways. Optimizing for average error fits the majority population at the expense of the minority population. And hiding group membership, racial attributes from the algorithm doesn't get rid of bias. In fact, it can be the opposite. Okay, so algorithms can be unfair. How can we make them fair? Well, in order for that to make sense, we have to define what we mean by fair. We can ask who was harmed. And one possible answer, not the only one, but one possible answer is that the people who were harmed were the qualified applicants who were mistakenly rejected. Okay, the people who should have been admitted to college, but who our algorithm mistakenly rejected. And if you like that answer, one statistic you might start thinking about is the false negative rate, which sounds a lot like the rate at which harm is done, if the people who are harmed are the false negatives. And so this is a popular definition, right? One popular definition of fairness is to ask that for groups that we care about, some error statistic, like the false negative rate, should be approximately equalized. Maybe that was what we objected to in this cartoon. There's many statistical fairness definitions, and if you'd like to come up with your own at home, you can go through this exercise. You can partition the world into groups, you can pick your favorite statistic of the classifier, and ask that that be approximately equalized across groups. There's a bunch of companies now that are willing to sell you products that will do things like this on your data set. And that's great, okay? But maybe it's not everything that we wanted. And here's just a quick example. Okay? Suppose I care about two things, race and gender. And so I've listened to the talk up through now, and I say I'd like the false negative rate to be equalized across blue people and green people and across men and women. Well, here's one solution that does it. I can admit to college everyone who's a blue man or who's a green woman. It satisfies my constraint, but it's cold comfort to the green men, for example, who will be rejected with certainty. So this is all to say that definitions are hard. I'm running out of time, so I'll skip the part where I try to convince you that there are ways to think about definitions in a more meaningful way, and get to the point, get to the main point. Okay? Whatever your definition of fairness is, once you have an algorithm that can satisfy it, okay? And all of these definitions have a quantitative knob. We can ask for something that's more fair or less fair. We can start to evaluate trade-offs. And one message from this field is that trade-offs are unavoidable. Okay, so once we have an algorithm that can not just optimize error, but can optimize error subject to some fairness constraint, we can say, well, okay, suppose I ask for suppose I ask for an algorithm, a model that's a little bit more fair. I will inevitably have to pay for that somewhere else, either in lost accuracy or more data. And if we're lucky, we can gain a lot in fairness while losing only a little bit in error. But that's not always the case. On other data sets, the Pareto curve looks different. So there's a lot more in the book, but what I want you to take away is that we have to be precise about definitions. Okay, we don't need to, that doesn't mean we need to hope to capture everything that people mean by words like privacy and fairness with an equation. You couldn't do that. But trying to capture part of those things helps clarify our thinking and helps discuss what we really mean. Once we fix a definition, we have to explore trade-offs, and we have to be willing to think in terms of trade-offs. The scientific question is to figure out what these trade-offs are, but figuring out where as a society we want to live on these trade-off curves, that's a societal question and something that doesn't have one answer. And the science is new and unsettled. We don't know very much yet. But we know that privacy and fairness are subtle and easy to get wrong, but possible to get right. So there's a bunch more in the book, but thank you.